Hello everyone. We are going to discuss this question from the inorganic chemistry. This is about the hydrolysis of different compounds, and we have been asked to find a compound which upon hydrolysis is producing tribasic oxy-acid as the final product. So saying tribasic oxy-acid means there is some compound which is having three OH groups present, and this is going to dissociate basically three H+ ions in the solution just from one molecule. So going forward, we'll see all these compounds, what is happening when they undergo hydrolysis. So BCl3, this compound, when undergoes hydrolysis, is supposed to be producing H3PO3 plus 3 times HCl. Although HCl can produce 3 H+ ions, but this is not what we are considering by tribasic oxyacid. So this is basically not an oxyacid only. H3PO3 is an oxyacid, but this H3PO3 does not dissociate to produce 3 H+ ions. The reason is this boron, which was having incomplete octet, when this is put in water, this try to pull electron from the oxygen's lone pair, and then something like this would happen, and ultimately oxygen will be pulling the electron from this is your boric acid being coordinated by the oxygen. This oxygen gets the positive charge, so this will be pulling electron from the H+. We'll be getting one H+ ion and BOH whole 4 that has a negative charge. So the idea is when we are going to react this H3PO3 with water, we don't get 3 H+ ions. We get only one H+ ion. This is supposed to be monobasic oxyacid. Now on the second compound, which is NCl3, when this compound is being hydrolyzed, HOH, here nitrogen's lone pair are relatively less available to attack onto the water molecule, so this is going to be attacked in chlorine's d orbital by this oxygen's lone pair, and those subsequent steps are giving us what we are knowing as NH3 and HOCl. Because oxygen goes into the lone pair of oxygen are going directly into the empty d orbital of chlorine. We understand chlorine will be forming bond with oxygen. So this is going to give us NH3 and HOCl. Although HOCl is an oxoacid of chlorine, this is having its basicity as only 1. This is not going to satisfy our condition. This is not going to be the answer. Then we are having PCl3. When this compound is undergoing hydrolysis, HOH, we are going to have H3PO3 and 3 times HCl. Again, HCl is not an oxoacid, H3PO3 is. So if you see the structure of H3PO3, this is going to be the situation. This is having possibility of producing 2 H+ ions, and this will be converting into HPO3 2-. This is having basicity only 2. This is again not going to be their answer. Going to the next compound, ASCl3. This compound upon hydrolysis will be producing H3ASO3 and 3HCl. The structure of H3ASO3 we could have expected to be exactly like H3PO3, but it is not. The reason is the pi bond which is being formed by phosphorescent oxygen can be fairly strong. As you go down, the size of the oxygen and arsenic may be changing a lot. Formation of a pi bond from the arsenic and oxygen may not be that much stable. And if you are having the stability coming from some different groups and some different atoms, that can possibly happen. This is the structure of H3SO3. So this is going to produce 3 H+ ions and arsenite ion, ASO3 3- ion. We might have seen this arsenite in number of redox reactions earlier, which converts into arsenate when there are strong oxidizing agent present, that is ASO4 3-. ASO3 3-, this which we might have seen, is already an indication that arsenite ion is going to be like there are 3 oxygen atoms which are having a negative charge present, something like this. If arsenite ion is this, arsenous acid H3SO3 is supposed to be having 3 OH groups present. This is our answer of this particular question. Now, when we are going for SbCl3, antimony chloride is going to react with water, and this is basically an equilibrium. And in this equilibrium, there is formation of SbOCl first, and 2HCl are being formed. As SbOCl is less soluble, this undergoes precipitation. Further hydrolysis of SbOCl is not possible, is not known to happen. Similar situation is known with BiCl3, which upon hydrolysis is supposed to be producing SbBiOCl, that is again producing turbidity or kind of white precipitate, and 2HCl. We are not getting any oxo-acid only in this case. So there is no point of, like we could have anticipated, just like ASCl3 here also Sb OH whole thrice could have been formed, or H3SbO3 could have been formed. These two compounds are behaving in completely different fashion, where the precipitation of this SbOCl as soon as it is formed is going to give you this compound going out of the solution. No further reaction is going to happen. So there is no any acidic hydrogen present in these compound. In the oxo-acid, HCl although is acidic, that is not the example of oxo-acid, because oxo-acid was the compound which is having hydrogen as well as oxygen. Now the last compound was FeCl3. When we do hydrolysis of this compound, we are getting ferric hydroxide, which is a basic compound. We don't believe this is going to produce 3H+ ions in the solution. So none other than our AsCl3 is going to give 3H+ ions. So that's the only tribasic acid we know in this, all the compounds which were given to us. So that's going to be the answer. Answer for this question was 1. Now, having known answer to this question, we may also require to go a little deeper into the concepts. What are all the concepts involved in this particular question? Here we go. So the first concept we understand is, whenever we are talking about hydrolysis, this is going to be mostly non-reduction. Mostly means it may not be all the time, but this is going to be in most of the cases non-redox change, where oxidation number of the elements do not change if you are doing simply hydrolysis. So we have few examples. So like BCl3 undergoes hydrolysis into boric acid and HCl, as we have seen already. PCl3, H3PO3 plus HCl. If it was PCl5, we would get H3PO4 and HCl. So if you see the oxidation number of nitrogen, if it is +5 in the reactants, it is +5 in the product. Here it was +3 in the reactant, it is +3 in the products. This is not changing, and this continues further. N2O5, nitrogen is +5, nitric acid is +5. SO3, sulfur is +6, H2SO4, sulfur is +6. This must have been H2SO4. IF5, iodine is in +5 oxidation state. HiO3, iodine is in +5 oxidation state, and fluorine is always -1. There is no question about that. In calcium carbide, carbon was each -1. So in the product, we are getting acetylene. Each carbon is having -1 oxidation state. In magnesium carbide, carbon was having its oxidation state of -3/4. In the product also, that C3H4 what has been formed, the oxidation state is -3/4 as it is in the reactants. Calcium phosphide, if you see, calcium is never going to change. Phosphorus was -3 each. So in the product, we are getting phosphine, which is having -3 oxidation state. In aluminum nitride, we have got aluminum always +1. Nitrogen was -3. So in the product, we are getting ammonia, which is having -3 oxidation state. So that is one of the important concepts for the hydrolysis of the inorganic compounds. We should be keeping the track of this thing. If this is a non-redox change, we should be getting the only product where the oxidation number of the product is not changing. And also we understand there are very few cases in which this is going to be a redox change. For example, we are having that first example is NCl3, where this is going to be a redox change. So see what is happening. In NCl3, nitrogen was having +3 oxidation state, and chlorine was having -1 oxidation state each. When this hydrolysis is happening, nitrogen is getting -3 oxidation state and chlorine is becoming +1. This was a redox change where the oxidation numbers of the nitrogen and chlorine are getting mutually interchanged. In NO2, nitrogen was in +4 oxidation state, and we know that nitrogen's +4 oxidation state is not very much stable. So when we do hydrolysis, this undergoes disproportionation into +3 and +5 oxidation states. Another such example is where xenon difluoride and xenon tetrafluoride are being oxidized. Xenon is in +2 oxidation state in the product. This is going to be 0. And fluorine is never changing. It was -1 here, it is -1 here as well. So if some compound is undergoing reduction, that xenon is going from +2 to 0, there has to be something which is undergoing oxidation. So water from oxygen is going from -2 to 0. We have not written water. We understand that water would be present over there. Same thing is happening to XeF4, where xenon was in +4 oxidation state. This is going to be in 0 oxidation state, and oxygen is going from -2 in water over to 0 over here, and same we can write over there. So these are very few cases in which the redox is also going to be the hydrolysis can also be redox, but these cases are very, very limited. One such interesting case we'll be finding here, where when BH3 is undergoing hydrolysis, this is converting into boric acid and hydrogen. In this case, it is not oxygen which is undergoing redox change, this is hydrogen. And if you know that in BH3, the oxidation states of boron and hydrogen are that boron is going to be +3 oxidation state, and hydrogen was in -1 oxidation state. So for boron, there is nothing changing. Boron is still in +3 oxidation state. So how we are saying this is a redox? Because hydrogen is changing to 0. But how is that possible? Hydrogen is in -3 in the reactant and product it is 0. How there is only oxidation possible? There must be something which is undergoing reduction as well, right? So what was that which is undergoing reduction? Because we will be reacting this with water molecules, and water molecules, some hydrogen were all in +1 oxidation state. So basically the hydrolysis of borane or diborane is going to be a calm proportionation. Water from hydrogen from water is undergoing reduction from +1 to 0, and hydrogen from borane is going to be oxidizing from -1 to 0. That's an interesting case of hydrolysis where disproportionation of hydrogen is known to happen. Okay, sometimes we can be seeing this kind of situation coming in organic compounds as well. We have few examples given here. So alkyl halide is replaced into alcohol and HCl when that reaction is happening. So whatever oxidation of this R was, this is retained. There is no change because Cl -1 oxidation state going out, OH -1 oxidation state can be coming in. And same thing can be happening in all other cases like geminal dihalide converting into aldehydes and ketones, chloroform converting into formic acid, cyanides converting into carboxylic acid, and ammonia. So in the cyanide, your nitrogen was in -3 oxidation state. In product also, nitrogen is -3 oxidation state. If we assume that R was hydrogen, then this carbon would have been in +2 oxidation state, and same thing over here, this carbon is going to be in +2 oxidation state if R is equal to hydrogen. If R is equal to some carbon, then this is going to change from +2 to here -3, sorry, +2 to +3. Then carboxylic acid is also going to change from +2 to +3. That has not changed at all. So this is how the hydrolysis of the different compounds we can see, and we can be seeing this is going to be a non-redox change, which whether we are whatever product we are expecting, we can be getting them from the hydrolysis. Consider the oxidation number of the atoms involved, which are involved in this kind of change. Okay. Now, the second concept for this question which we are supposed to be applying was that if you are having smaller second period atoms like your boron, or you can think of that carbon, nitrogen, and oxygen, all these elements, whenever they are present, then the presence of more than one polyvalent atoms mean to say we cannot have OH, we cannot have NH2. Also there can be one OH and one halogen. This combination is also not going to work. This is also, if you are having 3 halogens or 2 halogens, then this, because halogens are not polyvalent, they can be stabilized. So we know that compound CHCl3 exists, but we don't know a compound where say CH2 OH Cl. This kind of compound are not known to exist, or compounds like CH2OH, CH2OH, these kind of compounds are not known to exist. So this compound is unstable, this compound is unstable, this compound is stable. And that is what we are going to see. If you are having sp3 hybridized central atom, then more than one OH, more than one NH2, or one OH, one halogen, one NH, one halogen, these are all unstable situations, and that's because of the too much of the electronic crowding appearing onto the central atom. We also can see that later in our organic discussions when we talk about the formation of hemiacetals and acetal. Those compounds are not very much stable. There is an equilibrium. So that equilibrium is always favoring to where less repulsion situation is supposed to be present. We are having some examples. So if you are having H3BO3, you will see that in boron, in this case, there are 3 oxygen OH groups are present. How come this is becoming stable? The reason is this boron is now not sp3 hybridized, this is sp2 hybridized. So there is enough separation that this bond angles are going to be 120 degrees. The OH may not be that much sterically demanding, having those steric demand of the lone pairs to be requiring too much of the space. That compound is supposed to be stable. Same thing can be happening to the carbonic acid, where there were 2 OH groups present, but this bond angle was nearly 120 degree. So there is enough separation. Because this is sp2 hybridized, this situation, this concept is not applying into this particular compound. If you take other examples like H4CO4, now this compound is definitely not going to survive. The reason is, if you are having one carbon and we are having one OH, we have just seen that if we are having even 2 OH on one tetrahedral carbon, this is not going to be stable. This compound is not going to survive. This compound will basically be leaving one water molecule that will be easing out the repulsion on the carbon, and we can be getting this kind of products formed. And same thing can happen to the nitrogen when it was having, say, more than one OH groups. We have tried writing something like this, where there are 3 OH groups present, and then there can be one N plus O minus, just like nitrogen. Tetravalent nitrogen is going to be positively or negatively charged. This compound is unstable, and this is going to again lose one water molecule, and this will be converting into, after losing water, will be converting into HO, nitrogen, double bond O, plus minus. That is how this is converting into nitric acid. So this is unstable compound, this is unstable compound. They are converting into relatively more stable compound where repulsion is relatively smaller, right? Okay, one more concept related to the previous point only. If you are going from second period onwards, that's bigger atom, if they are present, they can have more than one atom present. The hybridization of the central atom can be sp3 or maybe sp3d, sp3d2, sp3d3, whatever kind of hybridization can there be, because bigger atoms may be relieving that electronic repulsion coming onto the lone pair of oxygen. So you can have now more than one OH possible. We are having some examples. This is your orthosilicic acid, where we can have 4 OH groups present like this. And phosphoric acid structure, we already know there are 3 OH groups present, although phosphorus is an sp3 hybridization. So these elements, central atoms, are sp3 hybridized, but there are more than one OH present, and these are stable compounds because central atom over here is going to be quite bigger. That can be relieving the strain coming from the interelectronic repulsions of the OH groups. We are having now arsenous acid. Arsenous acid is having 3 OH groups present, something like this, and that is what we have seen. This is going to produce 3 H+ ions in the solution, generating arsenite ion as the conjugate base when this is behaving as an acid. Okay, the same way we have got some other examples like this tellurium hydroxide, which is having 6 OH groups present, and this is basically we call orthoperiodic acid, which we might have used in the oxidation of geminal diols. So we have been writing that HiO4 as iodic acid. That was basically meta-periodic acid. This is called meta-periodic acid. Its structure would be I double bond O, 1 OH, 1 OH, 1 OH, another OH, and one more OH. So there are 5 OH groups present in total. That is going to be the structure of this. Because iodine is huge, it can stabilize 5 OH without any problem. That is the structure of this particular compound. That is what we are seeing. Bigger atoms can stabilize more than one OH groups. Smaller atoms may be finding it difficult. Next concept we are having about this hydrolysis is, if we are having oxo-acids of oxygen, then in all the oxo-acids there is at least one phosphorus oxygen double bond present, and this oxygen double bond is going to be, phosphorus oxygen double bond is actually very stable. We know this is one of the very stable bonds between any two elements known. Although we are having carbon oxygen, it has an oxygen bond very much stable, but if you talk about the phosphorus oxygen bond, that's also lying onto the higher side of the bond energy values in comparison to most of the other element bonds. So in the orthophosphoric acid, we have seen the structure. There's one PO bond present and 3 OH present. Phosphorus acid, there is one PO bond and there is 2 OH groups present. In H3PO2, we are having again one PO bond, and then there are two hydrogen bonded to phosphorus directly and one OH group is present. So whatever be the oxo acid of the phosphorus, P double bond is definitely going to be present. That is because of its greater stability, and molecules always tend to more and more to go towards more and more stability. They will never go towards a state where it's going to be less stable. Right. The last concept we are having for the hydrolysis things, which can be applied in a number of different situations, is if we are having bigger atoms, like we talked about arsenic and antimony, where we are having the hydrolysis. This is a hydrolysis in equilibrium. We talked about this equilibrium already. So the interesting outcome of that hydrolysis is, if you are not having further hydrolysis possible, we cannot have these compounds produced. If these compounds are not being produced, before that SbOCl and BiOCl, which are being formed, they are undergoing precipitation. So that precipitation of these SbOCl and BiOCl makes that they are becoming soluble in dilute acid, because that equilibrium which was there, if you are having HCl onto the product side and let us say SbOCl over here, you are having say SbCl3 and water. So this compound is soluble in water. This compound is insoluble in water. So this is an interesting case where putting water, like making it diluted, is going to give you precipitation. And if you are putting HCl, this is going to dissolve the things. This is something we have not seen in other cases, but this is very interesting case where the partial hydrolysis of the arsenic and antimony chlorides is resulting into the precipitation. That precipitation is seen as turbidity. Okay, so I think that is a very long discussion covering many of the concepts which can be applied to a variety of the situation, and I hope that can be pretty useful to you if you are applying this to the hydrolysis of any other compounds given to us. And I think most of the questions which are based on the hydrolysis you can possibly solve if you have followed this video correctly. So I think that's all in this video. See you next video. Thank you. Bye bye. Take care.